In the previous video, we saw the ergodic theorem for Markov chains, and now we need to define what these terms that we used in the statement of the theorem mean. So one thing maybe I should have mentioned is that a Markov chain, a discrete Markov chain, which satisfies the properties that it's irreducible, has a stationary distribution, and is aperiodic, is called an ergodic Markov chain. So that's why it's called the ergodic theorem for Markov chains. And let's define some of these terms. So the first term that we need to define is time homogeneous. So we say that a Markov chain xi, using our shorthand here, is time homogeneous if we have the following property. If the probability that xi plus 1 equals some value b, given that xi equals some value a, equals a number tab, and this is for any I from 0 to, from 1, I guess 0 to n minus 1, and for any a and b in x. So this is the important part. This is for any I, and this is for some matrix T. So take all these numbers tab and throw them together into a matrix T. So the important part here, the reason why it's called time homogeneous, is because these conditional probabilities, these transition probabilities, as we call them, do not depend on time. They do not depend on I. Usually when we have a Markov chain, we think about I, the index, as time. It's sort of running forward in time. And another thing I should mention here is that this matrix, I called it a matrix, and usually when you think about a matrix, it's like a finite matrix. But this matrix is, it could be infinitely large. So when this x here is countably infinite, if the set of possible values that the xi's are taking is infinite, then this is going to be an infinite matrix T, because we have to have a value for every pair of states in this X. And this T is called the transition matrix. So that's just a little terminology. This T is the transition matrix, and it is what's called a stochastic matrix, meaning that all its entries are non-negative, and the rows of the matrix sum to 1. So the rows are the sum over b, tab, sums to 1 for any a. That's called a stochastic matrix, and this is for a discrete Markov chain when it has a discrete space. And more generally, when you have a continuous space Markov chain, the transition matrix, it's a stochastic matrix, and it gets replaced by a stochastic kernel, which is just a function on the product of x with this space x with itself. It's just a kernel. I mean, it's just a function. Call it a kernel. All right, so that's the first definition, time homogeneous. And what else do we need to define? We need to define a stationary distribution. So let's do that. A stationary distribution. Definition. A PMF pi on this space, this script x, is a stationary distribution, stationary dist, or sometimes people say invariant distribution, and you'll see why in a second. Invariant. So pi is a stationary distribution with respect to t. Usually we don't say that, but just to be precise. So it's a stationary distribution if it satisfies the following property. If pi t equals pi. And what the heck does that mean? Here, what this notation means is that we're thinking of pi as a row vector. So t is a matrix, right? We're thinking of t as a matrix, and we're thinking of pi as a row vector. And so we just do the linear algebra sort of thing. We multiply this row vector times this matrix, times the the columns of this matrix, and we get back another row vector. And it turns out here, for when it's a stationary distribution, the row vector we get is pi. So in other words, what this is saying is that when we sum over all values a, pi a times tab, we get back pi b for any b in this space X. So this is sort of generalizing, this is sort of using a more general notion of matrix multiplication, since it could be infinite vector here. And you may recognize, or it may sort of be popping up in your head that this looks sort of familiar. If you know your linear algebra, then you may be sort of thinking that this might be reminding you of an eigenvector equation. And in fact, this pi is called a left eigenvector, and it has eigenvalue 1. So it's a left eigenvector with eigenvalue 1. Okay, so we got a stationary distribution and a time homogeneous Markov chain. And what else do we? Let's go back up here. What else? So we got stationary, we got time homogeneous, and we need to define irreducible. So let's do that next. Irreducible Markov chain. We'll take a look maybe in the next video at some examples to make all these concepts concrete. A Markov chain, xi, that's xi, is called irreducible if for any pair A and B in the space X, there exists some time t such that the probability that xt equals b given that x0 equals a is strictly positive. Any a and b. So in other words, no matter what a we start out at, no matter what a x0 is set to, and no matter what b we're trying to get to eventually, for some time, eventually we're going to get there. So there's some positive probability that we'll get there. I mean, we might, this isn't saying that we definitely will, but this is saying that with some positive probability that at some time we will get to B. So there's at least a positive probability of it happening. So intuitively, you could think about that, B can be reached from A. If you start out at A, then you can reach B. So if we were to draw sort of all these possible states, this were all the values of that X space. Maybe this one's A and maybe this one's B here. And this was time if we copied this space. 0, 1, 2, and so on. We start out at A, then maybe we go to this one, and then we go to like this one. That eventually, for some time t, there's a positive probability. So there's some path here that has positive probability in which we eventually get to this state B here. This is state B. And it has positive probability in the sense that when you multiply together all the transition probabilities for going to A, from A to whatever this is, and then this to whatever this is, that there's a path from A to B that has positive probability. The product of all those is positive. So that's irreducibility, and we need to define, I think there's one more. So we got irreducibility, we got time homogeneous, we got a stationary distribution, and we need aperiodic. So what is an aperiodic Markov chain? This one is maybe this is maybe the least intuitive of all of them. Maybe at first. You have to get your head sort of wrapped around it. So an irreducible Markov chain, xi, is called aperiodic if for any a in the space X, we have the following property. The greatest common divisor of the set of times t for which the probability, this probability is, well, not exactly that probability, for which the probability that xt equals a, given that x0 equals a, is positive, the greatest common divisor of this set of times equals 1. That's a 1. Now that's sort of a mouthful, or a headful to get your head wrapped around. So let's break it down. Let's think about what this means. So let's define, so let's define this set of times here to be, let's call it RA. Depends on A, the state A. These are all the times where, starting out at A, we can get to A again with some positive probability. So let's say this is time 0, 1, 2, 3, 4, 5, etc. These are all times. And let's mark down, so if this is, the line here, let's just put a dot wherever we can get there with for all the times that we can get there with positive probability. So maybe we can't at 1, but then 2, 3, 4, not 4, and then 5, maybe 7, and so on. So these are all the times in this set RA. And now let's also define the set MK, sets MK, to be the multiples of k, of the integer k. So k will be a positive integer. So in other words, this is just all the numbers, let's say jk, as j ranges over, let's allow it to be all the integers. Doesn't make a difference. So these are all the multiples of k, all the integer multiples of k, where k is some integer. Let's make it just positive integers. So we'll just define this for m1, m2, and so on. But we allow all the multiples. And then if we look at these, m1, m2, and m3, well, what are these? m1 is all the multiples of 1. So if we're looking at these non-negative times, of course, all these elements are, all these numbers, every positive integer is in it. Every integer is in it. For 2, m2, we have all the multiples of 2. So this is obvious. And for 3, we have all the multiples of 3. So that's clear. And what is this saying? So now that we have sort of this picture in our heads, what is this saying? So first observe that RA, this set of times, this set here, is contained in M1, right? That's obvious. Every time here is an element of this set. But it might not be contained in the other ones. And what this is saying here, this condition, this is true, the greatest common divisor is 1, if M1 is the only set that of one of these, M1, M2, M3, M4, and so on, that contains RA. Because if RA is contained in MK for some k greater than 1, then k divides every element of RA, and so the greatest common divisor is greater than 1. And on the other hand, if the greatest common divisor is, say, k for some k greater than 1, then RA is contained in MK, contained in all the multiples of k. Okay, so that's aperiodic, and that wraps up our definitions of the conditions needed for the ergodic theorem for Markov chains.